Okay, so good day everyone. So today we're going to discuss about binary others. Okay, so binary others, these are arithmetic circuits in the form of either half others or full others. Okay, used to add together two binary digits. Okay, so this is one of the functions of binary others. Okay, especially when you're going to make arithmetic circuits, no? So we're going to use others. So the basic binary other circuit can be made from the standard and XOR gates, so allowing us to add two single bit binary numbers A and B. So take note that when you are going to create an arithmetic circuit, especially when you're going to add 2 bits, so we're going to use the binary adders. So binary adders is basically made up of these two basic gates. So remember before that I already gave you an assignment regarding regarding the basic gates. So the basic gates that involves in creating a circuit for binary adders is the AND gate and the XOR gate. So you will see later on the diagram of others. Okay, so others, it is a two type. We have the half other and we have also the full others. Okay, so the output of the sum of the two digits being added produces a second output, which we call the carry or carry out or C out. Okay, so if you're going to add two digit, so for example 1 bit, okay, so the resulting value will give you a carry value. So remember in our arithmetic of binary numbers, diba? So the rule in addition of binary in logic is the same rule, no, when you're going to add binary numbers. So one of the main uses of binary other is in arithmetic and of course in counting circuits. So this is now the block diagram of the half other. Okay, so you have inputs A and B. Okay, wherein the values of your A and B could either be ones or zeros. Okay, so here you have two outputs here. The output is the sum. Okay, if you're going to add 2 bits, the result will be here, it will come up here in the sum section, and of course if there are carries, so it will go out in the carry output or the C output. Okay, so it's just like having this one, in the diagram you have A plus B, the result will be the sum, and of course if there will be an extension to the result, that will be in the carry output. Okay, say for example if you're going to say 1 plus 1, okay, so the result will be 1 0, so therefore your 0 will be your sum and your 1 will be your carry. Okay, so that's the basic diagram of or block diagram of half other. So if you're going to look at here, diba, you have this one block diagram. So what is the circuit inside your half other? Okay, this is just only a box, a representation of half other, but inside this box contains the circuit, no? So what is the circuit inside the box? So this is the equivalent circuit, no? As mentioned earlier, that the other is basically made up of XOR gate, and of course it is made up of an AND gate. So combination of the two, that will give you this particular circuit. Okay, so these are your inputs A and B, and this is now your XOR gate, okay, which carries now the sum, and of course your AND gate now, which carries the carry out or the carry output. Okay, so say for example if your inputs here will be A is equals to 0, and of course your B is equals to 1, of course the result is the sum is equals to 1, and of course the carry will be 0. But if you're going to put here 1 0, okay, 1 ang A, B is 0, then the result is ang sum niya is 1, and then the carry is 0. But if you're going to put here, say for example, the input for your A is 1 and the input for your B is 1, so 1 and 1, okay, and 1 XOR 1, the result is 1, of course, and 1, the result will be 0, okay? The result will be 0 because this is inverted, no? Inverted siya. So, the result will be 0, and then 1 and 1, the result is 1. So, the result will be, ang carry niya is 1, and the sum is equals to 0. Okay? So, again, take note of the truth table of each logic gates. So, I gave you an assignment already regarding the basic gates, not only their names but also their symbol, what are the symbols of those different basic gates, as well as their truth table. Okay, because it is important for you to know the truth table so that you'll be able to know the outputs, no, if these are the particular inputs. Of course, our inputs will only be ones and zeros, but depending on the particular gate that you're using, so it will make a difference when it comes to your output. Okay, so next we have this one. So again, we just try to simplify, no, these two, because we have this one, the XOR, and we have this AND gate. So for the XOR gate, again, as I've said, that I already gave you the assignment, and then not only the particular symbol but as well as the truth table. So if you're going to look at the truth table of the XOR gate, okay, so you have, if your inputs in your A and B are zeros, then your output is 0, because this is normally inverted. Okay, inverted siya. So if the input is 0 here, okay, or yes, 0, and then it will be 1, and then here may invert na po yung 0, yes, and then therefore na 0 0 siya. So what will be the output now is equivalent to 0. So if the input is 0 here, okay, kasi take note that these are inverted, so the input here is 0 1, so the output is 1. Okay, so obviously if the inputs are 1, may mo siyang 0 kasi invert lang niya 1 1, invert niya 0 0, so that will become 0. Okay, so next we have this one, the 2 input AND gate. Okay, so 2 input AND. Okay, by the way, when it comes to input, so we're only using the most basic, no, which are 2 inputs. Usually we're dealing with 2 inputs, but the particular ICs that we're going to use does not only deals with 2 inputs, but there are also other ICs that the same, no, like for example AND gate or XOR gate that has multiple inputs. Say for example 3 inputs, 4 inputs, or it could be 6 inputs, no, it depends. But again, the IC number for that will be different. Okay, so lahat na po ito siya IC number. But what I'm trying to say is that when it comes to inputs, so we are not limited to 2 inputs only, because there are also ICs with the same logic name, okay, gate name, but are multiple inputs. Okay, it could be 3 4 5 or 6 inputs or more than that. Okay, but of course, as again, the IC number will be different. Okay, so the same na basic, we have the AND gate and we have the truth table for AND gate here. So okay, just familiarize the truth table so that you'll easily identify the output. Okay, so now if you're going to combine the two, okay, if you're going to combine the two, you're going to have this particular output. Okay, this will now be equivalent to half adder. Again, the combination of the XOR gate and the AND gate. So the AND gate carries now the carry output, and the XOR gate carries the sum output. So based on the given truth table, if you're going to add A plus B, so A, which is 0, and B is equals to 0, so therefore the sum is 0, the carry is 0. If A is 1, B is 0, therefore the sum is 1, the carry is 0. Okay, so for you not to be confused with this one, so just follow the basic rule in addition. Okay, like what we had in our arithmetic of binary numbers. So 1 plus 1, obviously that is 1, 0. So therefore, your carry here is your 1, and then your sum is equals to 0 here. Okay, so that is the function of the half adder. Okay, from the truth table of the half adder, so if you're going to look at the sum, okay, the result of the OR gate, and of course the AND gate now carries the C out, or the carry out output. Okay, so mo ni siya, no, ang iyahang explanation. So sum is XOR A XOR B. This is now the symbol when it comes to Boolean expression. Okay, in the Boolean expression, we're just okay. For this one, the dot is AND. Of course, if you're you're going to use the plus, so that means that is OR. Okay, OR. Pero in the symbol for Boolean expression, so mo ni siya, no, kaning circle tapos na plus sa tunga. So mo na ang symbol sa XOR gate. So again, be familiar with the symbol used in the Boolean expression, because you know the Boolean expression now, which you were able to derive from the K-map, no, if you're going to simplify your equations tapos magkaroon ka og XOR na result, then you'll be able to identify the equivalent logic gate, no, based on the given symbol sa imong Boolean expression. So this is the symbol for XOR gate, and this is the symbol for AND gate, which is the dot. Or another thing for this one is, if you're not going to use the dot, you can use the open and close parentheses. That will mean that you are using the symbol or the expression that is being used is the AND gate, okay, or the AND logic gate. Okay. So full adder. So the main difference between the full adder and the previous half adder is that full adder has 3 inputs. Okay, so na 3 inputs. So usually on full adders, why it has 3 inputs? Because the first input are the 2. You have the A and B, and of course the second or the third input refers to the C-in. So C-in, it refers to the carry output of the previous, it could be half adder or previous full adder. So the carry out of the previous full adder will be the carry in of the next full adder. Okay, so mo to siya ang carry in. So I will show you the diagram. Okay, so this is now the block diagram of the full adders. So again, we have inputs A and B, and then the C-in. Okay, there are 3 inputs. For your half adder, you're only going to consider the 2 inputs, but in the full adder, you're going to consider the 3 inputs, because this one, as I've said, the C-in here, okay, the third input will be the this will be coming from the output of the previous full adder, which is this one. Okay, if you have another full adder here, so this output will be connected to the C-in of the next full adder. Okay, but the same, you have the same output, no, when it comes to output, you have 2 outputs. We have the sum and also the carry out as your output. Okay, the full adder is the logical circuit that performs addition operation on 3 binary digits. Okay, 3 binary digits. You have the A and the B, and of course you have the C-in. Say it also generates carry out to the next addition column. So the carry in is the possible carry from the less significant digit, while the carry out represents the carry to more significant digit. Okay, so this is now the block diagram of the full adder. So a full adder is just a combination of the 2 half adders. Okay, combination lang siya sa 2 half adders. If you're going to look at the block diagram here, you have inputs A and B. So the sum is you have A XOR B. that will now be inputted to the inputs of A and B to the next half adder. And of course, the this one the output of the input here in the CN will be the input to your next input here sa second half adder, which is your B. Okay, so if you're going to look at here, this output of this one will be A XOR B, which is this one, of course, and XOR CN, which is this one. Okay, kanina iyahang XOR CN, that is for the sum. And for the carry, if we're going to look at the carry, there will be two carries here to be ORed. Okay, so this one is the carry A and B, which is the result of your input A and B here. Then that will be OR to the carry of the CN, A or B. So this one, A or B, kani siya will be ANDed to this one. Okay, kaning CN. So CN and A XOR B, that will now be the carry out. That will be also ORed to the carry of this particular half adder. Okay, so wala siya karon imong C out. Again, duha lang gyapon, and then but inside the block of your full adder are two half adders. Okay, two half adders. So just take note of this diagram. And of course, again, as I've said, that inside your half adder is a combination of an XOR gate and an AND gate. That is why if you're going to look at the output here, if you can see, CN is being ANDed to A XOR B. Okay, A XOR B. So kadua na siya nag-XOR because this one is the first half adder, this one is the second half adder. So the output of the first half adder will be cascaded to the next half adder. Okay, that is why you have here A XOR B, and then XOR C and CN. Okay, take note for the sum, the gate that you're going to use here for the sum is the XOR, and for the C out, okay, the gate that you're going to use here is the AND gate. Okay, so again, this is the circuit diagram. Okay, this is the first half adder, this one is the first half adder, and this one is the second half adder, this portion here. Okay, muning kadua nga half adder. So again, the output of the A or XOR B will be the input of the XOR of the second half adder, and also the CN will be the input of the XOR of the second half adder. And of course, you're going to AND the two. The result of the AND here will be ORed with the result of the AND of the first half adder. Okay, that will now be your C out. Okay, so if you're going to combine, those two half adders, you will come up with the full adders. So if you're going to look at the truth table of the full adder, okay, you have the CNs, B and A. These are now your inputs, and your outputs now are the sum and the C out. Okay, so here if you're going to add the 3, that will become 1. Okay, if you're going to add this 2, that will become 1 0. Okay, the sum now, okay, taking the sum, that is the result, and the carry will now be the katong extra niya, no, if you're going to add the 2 bits na binary numbers. And you have A 0 1 plus 1. Of course na siya carry because 1 plus 1 na siya 1 0. So ang 1 will be the carry and 0 will be the sum. Okay, 1 0 yapon, of course. Okay, 1 plus 1 again, that will be 0 1. Okay, okay, so this is now the full adders now that is being cascaded. So naka-cascade na siya. So there are two inputs, A and B. So this is an example of 4-bit. Okay, 4-bit siya na binary adders. Okay, so from A0 to A3 and then B0 to B3. So this is a 4-bit binary adders. Okay, A0 and B0 are the LSB or the less significant bit, and the A3 and the B3, these are now the most significant bit. So this is the least value, this is the most significant bit pala. So if you're going to have this binary, so muna siya ang 1, 2, 4, 8. Okay, 8 ang value sa MSB that is equivalent to A3 or B3. And the value of your A0 and B0 is equivalent to muna siya ang 1. Okay? So again, these are now the block diagram of the 4-bit binary adders. So later on, we're going to have examples on this one. Okay? So again, this will now be the equivalent. Actually, there is already an equivalent IC for this one. So the good thing is, natin available ng IC, which is the 7483. So 7483 is a 4-bit full adder. Okay? What you're going to do, this is now an IC. No, siya na siya ka-IC. So mag-input na lang kadiya. So if this is not, if you're going to break this one, no, i-break nimo ni siya. Just imagine how many AND gates and how many XOR gates you're going to use. Because these are full adders, and in one full adder contains two half adder, and a half adder contains the basic one AND gate and one XOR gate. So pila sa isa ka full adder, you're going to make use of two AND gates and two XOR gate and one OR gate. So 5 na ka IC daan. So 5 ka IC sa isa ka full adder. Pila ang kailangan ng mga full adder o path. So 20 ka IC, no? 20 ka IC mo kailangan. So nga na siya kadaghan, but in this case, now we have already a 7483, which is a 4-bit full adder. So equivalent lang siya sa isa ka IC. Okay? Sige lang, we're going to have an example of how we're going to add 2 bits or 2 binary how to add binary numbers using logic circuits. Okay? So I'm going to use a Proteus to give you an examples, no, on how we are going to actually implement a binary adders using our software na Proteus and using also the basic gates that we have. Okay? So I think that's all, and I'm going to give you an example later on. Okay? Thank you everyone for listening.